So, welcome everybody to the second episode of the ML Papers. Let me first, for those of you who might be here for the first time, tell you about what this campaign is about, and then we'll jump right into the well to the topics, and then we'll begin with our paper. So, this ML Papers is a campaign that was initiated by the Google developers team. This is the same team that manages the ML experts group and the TensorFlow group. So they invited BigNumber to participate in this event, and also it's in collaboration with deeplearning.ai. And speaking of deep learning, I want you to, if you haven't yet, check out the description, the full description of this event, because you're entitled to a discount for any course on Coursera. Now, this campaign is about reading some of the most influential papers in machine learning. So it's supposed to be a group effort, So even though I'm going to be speaking and taking you through the highlights of this paper and all of these papers for that matter, the idea is to encourage participation by everybody in learning these research papers and then hopefully even contributing to machine learning research. Let me just jump one slide ahead just so I can show you the papers that we will go through. So this is the second episode. The first paper that we looked at was zero-shot learning through cross-modal transfer. You can see the recording of this on our YouTube page, and you can also find it on the BigNumber website. The link is also in the page where you RSVP'd. This paper, of course, like it's already listed in the event page, is Introduction to ROC Analysis. And then, of course, you can find the other papers that we'll be going through in the slides once I share the slides with you. And I'll do that after the session is over. Now, this session is 1 hour and a half in duration, but I will give you an hour and a half, towards the last 15 minutes of the session. If you have any questions, I'll be here to answer them for you. Although, if you have any questions at any point, you can always leave them in the chat. I have them here on the other screen so I can see your questions when you put them in. Okay. ROC stands for Receiving Operating Characteristic. It's a form of graphing for machine learning metrics. Machine learning metrics are an empirical way to measure the performance of a machine learning model. Now, the ROC curve in particular is about classification machine learning models. So here's how we're going to go through this session. First, I'll give you a quick overview of machine learning classification metrics, because the prerequisite for understanding this ROC analysis is, of course, some basic measurements of classification. And then we'll go through the items listed in the paper. So everything from classifier performance all the way down to interpolation of classifiers. These are the 11 sections of that paper. And this paper is 14 pages long, 13 pages if you want to exclude the references. So it's somewhat lengthy. So we're not going to go through every single item, but I'm going to try to highlight every important point from these sections. So let's begin with the preliminaries. So a machine learning model, very quickly, is an algorithm implementation of some sort of statistical technique. Okay? Where you have your features, that's your input, and the algorithm learns the parameters of these features, and then you get an output, which is what we call the label. Now, we have different types of machine learning models, right? Supervised, unsupervised, reinforcement learning. But the machine learning models that we're going to not the models actually, but the classification of such models or classification models. Like a machine learning model can output three types of outputs. If it's regression, for example, these are examples, these are not actual values. If it's regression, it will be some sort of quantity. If you're going to forecast the value of something. In the case of classification, it will be either a class, like a binary class, or the labels of a class, or it will be an entire distribution. And if you were to add up all of these values in this set of values, it would add up to 1. The ROC curve is used to both analyze the performance of a binary classification model or a multi-class classification model. So if you have a classification model that is meant to detect something that is fraudulent or not fraudulent, spam or not spam, these are binary classification examples. Or if we're going to classify, let's say, type of illness. What kind of illness is it? Is it inflammatory? Is it related to the skin? Is it related to vision? So if you have multi-class classification, also with the ROC, you are able to measure and analyze the performance of this model. Ron asks, is this called a normalized distribution? Not necessarily. Now, speaking of distribution, ROC, now this is something that is highlighted at the very beginning of this paper. Now, one of the advantages of ROC analysis is that it is not affected by the skew, the class skew. If you probably know what a normal distribution is. If you look at this graph, this is not normal because it's slightly skewed to the right. Okay, whereas a normal distribution has this classical bell curve. Now, whether it's a normal distribution or a non-normal distribution, or if you want non-parametric distribution, and even if it's skewed, heavily skewed, you can still use the ROC analysis. Now, what's an example of a skewed distribution? Fraud. You see, if you look at a data set for financial transactions, most of those transactions would be legit. Let's take a data from one particular bank. Most of those transactions would be legal. But a very small number of them will be fraudulent. So if you were to look at the distribution of this data, it would be very skewed, and then it might rise sharply at at the ends of the distribution. If that's not clear, once I'm done with these slides, I'll show you pictures on Google to make this clear to you. Okay? So the point here is the ROC is very effective with all kinds of classification models. So whether it's a naive-based classifier, logistic regression, neural networks, what have you, the ROC analysis is quite relevant. Okay, that's actually the end of the slides. That's all I have for the slides, because the rest of it, what I'm going to do is I'll take you through the paper. That's right here. And where necessary, I'm going to write some mathematical expressions, because this paper like I said, this paper assumes that you know the prerequisites, and I might have to give you some context. So I'm going to switch to VS Code, Markdown in particular, to write some expressions to hopefully give you clarity. Okay, so we have, how many sections we have? We have 11 sections. The first section just tells you about the deduction, for example. It is for comparing classifiers. You can actually compare multiple classifiers to each other. You can interpolate the graph of two classifiers. Maybe one does better in one area, another one does better in a different area, and you want to kind of get the best of both worlds so you can arrive at a third classifier given the curves of your two original classifiers. So the introduction section talks about that. And again, here it says, Especially useful for domains with skewed class distribution and unequal classification error costs. Now, what does this mean here? Let's actually start here. Domains with skewed class distribution. Again, these are data sets in which one class, even if it's a binary class, the other class happens infrequently, like fraud or rare diseases. You know, if you're trying to use a machine learning model to predict if someone has like a malignant skin condition, first of all, it is relatively rare for patients to develop such conditions, relatively speaking. However, if it does occur, if a person does have a malignant skin condition or a malignant any condition, the cost is very high. Unequal classification error cost. So again, if you take fraud, for example, yes, fraud happens infrequently. But when it does happen, it is disastrous because it can happen in large amounts. Several millions of dollars could be lost if it happens just at that one time. So we have to be very careful if we're going to be using a machine learning model in production and we are not thorough with our machine learning metrics and we put this into production, and in particular when we're dealing with domains, like this paper says, skewed class distribution, it can be quite problematic. So with ROC, we have an effective way, not the most effective, but it's one effective way for detecting such problems in models. And then it says ROC graphs are conceptually simple. I'm going to skip that. Now let's talk about some of the basics before we proceed any further. So we have classifier performance. All right, now let me also start here for section 2 with some notation because we have over here a confusion matrix. So I need to, especially for those of you who may be new to these metrics, give you some clarity. So I'm going to switch here to VS Code. What I do is basically, let me show you what I'm going to do. I'm going to open a new file here. I'm going to save this on my desktop. ROC.md. Basically, I use Markdown to write down math expressions. My handwriting is, not very good. So what I do is I write Markdown on the left, but you want to look here on the right. Okay? So for section 1, or section 2 rather, the classifier performance. Let me close this window. The paper uses the notation C for a class. One more time. C for a class. And I'm going to use a mapping notation. So we have I for instance. And this C, the C here stands for a classification model. Basically, it maps an instance. An instance can be an observation in your data set to an element in this set, which could be either P or N. P or N, where P is a positive class and N is the negative class. So for example, again, if we're talking about fraud, P could be a vector of values corresponding to the distribution of a fraudulent transaction, and N could be a vector corresponding to the distribution of a non-fraudulent transaction. Okay, now let me also add section 1 because we can't go farther, we can't go past this section unless we know what these are, why they are relevant to the ROC curve. Okay, because the ROC curve, if I scroll down here a little bit, you can see on the x-axis we have this thing called the false positive rate, and on the y-axis we have this thing called the true positive rate, and we have some synonyms here. So I'm not going to show you these because, again, the one I'm going to show you hopefully is simpler to interpret. Okay, so let's begin with these things called false positive, true positive, sensitivity, specificity, which are not written here, but those are nonetheless synonyms for some of these metrics. Okay, section 1, let me show you. Let's first talk about how we measure the performance of a model. So we have something called true positive, the true positive rate, and the false positive rate. Okay. Something that is true positive. When we say true positive, we mean something that the model has classified correctly. So if we're talking about fraud, then a true positive classification is when the model correctly classifies something as being fraudulent. And the true negative classification is when the model correctly classifies a transaction as non-fraudulent. Because that's what a model should be able to do. It should be able to distinguish between fraudulent and not fraudulent correctly. This true positive rate has other synonyms, namely sensitivity and recall. So if you come across these in other papers or books or even blogs, know that they refer to the same thing. But let's just focus on TPR. It's a true positive rate. So the true positive rate is the number of correct. Okay, let's say you have a data set with 10 observations. And 9 of them are, instead of fraudulent, let me use a different example. 9 of them are, let's say, we use colors, red and blue. Okay, 9 of them are blue, 1 of them is red. Okay, so let me zoom in first so you can see this ratio better. If the number of false negatives is 0, meaning the model did not misclassify any of those colors, then this ratio would be equal to 1. Right? Because Fn would be 0, this would cancel out, and TP over TP, that's just 1. So its true positive rate will be 100%. But every time the model falsely classifies or misclassifies an instance, Fn is going to go up by 1. So for example, let's say here we have 48 over 48. 10 of those classifications were done incorrectly, which is why when we evaluate this ratio, the number starts to drop below 1. So sensitivity is a number, by the way, between 0 and 1. Okay? So that's what this is trying to encapsulate. Similarly, specificity looks at the the idea is the number of false positives. How many false positives has this model classified? Again, if this number of false positives is equal to 0, then FP is eliminated, and then we have Tn over Tn, which is again 1. And that's ideally what we want. We want this model to have 0 false negatives and 0 false positives. So its sensitivity is 100%, and its specificity is 100%. Okay? And this is what we're going to plot on the ROC curve. If I bring you back to the paper, down to, for example, this picture, false positive rate, otherwise known as, well, there's actually one more. There's actually a couple of them. I'll show you, I'll take you to Wikipedia later on to show you all of the other metrics. False positive rate, let me copy the expression I have here. Just a second. Sorry. Okay. And I'm going to actually open up that page from Wikipedia. But we don't need to look at all of them right now. We don't need to make it too complicated. Let me just find that page. I closed it by mistake. Yeah, here we go. Again, we don't want to look at all of these metrics, but these are the different metrics that we're going to use to look at the performance of a model. So false positive rate is given by this expression over here. Okay, so this is going to be on the x-axis. This is also what we call the cost. Obviously, if the number of false positive is too high, then the model is making too many costly mistakes. Let me actually write this down here. Let me include this here. So we have FPR. Again, you want to look on the right panel. So the false positive Tn. So this is the x-axis, also known, or what the paper calls the cost. And if we're going to use cost benefit terminology, then in the case of the ROC curve, the benefit, if that's the cost, the benefit would be the TPR. So also the recall. Okay. Now don't worry about the other metrics, but we will have to return them. I know that recall is also in other examples. Some have struggled truly understanding what recall really means. So if time allows it, I'll also give you an example. I will build upon these metrics one by one. Okay. And as you can see here on the left, there are different ways to express those same ratios. But let's stick to the ones I showed you there because that is easier. Now, if you look here, in section, let's see if section 2. Yeah, let's actually stick. Let me also walk you through the confusion matrix very quickly. And give you an example from Google to show you how this is interpreted. Confusion matrix. Now, there are two types of confusion matrices. One of them is for binary classification. The other one is for multiple classes. Let's begin with a binary example first. This is actually a good one. So if you look at this, here's how you're supposed to interpret a confusion matrix. These are, on the rows correspond to the true labels of the data. And the columns correspond to the number of labels that the model predicted correctly. I'll give you an example. So I don't know what this example is about, but let's say it has to do with I guess these numbers are too great to be fraudulent, but let's use fraud. Let's use fraud anyway. Okay, so the number of actually fraudulent transactions, you know what, these numbers are too big. Let me use a different example, something that is less skewed. What's an example? Let's use property. The model has to classify a property by whether it's a residential property or a retail property, for example. So let's say 105 of the properties are retail, but the model predicted only 100 of them correctly. So that's 100 over 105. So it's the ratio is 95%. So when you see a table like this, in the case of a binary model, you take the cell in the true positive, which is in here in the bottom right, divide that over the total number of true the actual true positive, so the actual correct number of, let's say, retail properties. And the same is true if you're doing it for false positive. Now, of course, in this paper, the axes are actually flipped around. So in the picture I showed you, the true classes were the rows or horizontal, whereas here, the true class is vertical. Okay. Again, if this is not clear, towards the end, I will return and give you an example, a more complete example for both binary classification and multi-class classification. This is not difficult to interpret. Now, F measure, this one we do really to appreciate F measure. It's best to see how this is derived. But F measure is actually the harmonic mean of precision and recall. Let me skip this for now because it is not necessary for us to interpret the ROC curve, and I will come back to it wherever we see it in the paper. Okay, but we will come back to this later on. Now let's talk about the ROC space. First of all, the word space. The word space means set of points. And if we look at this figure to which this section is referring, this is it's like a Cartesian coordinate system, and we have these points A, B, C, D, E. Now, let me zoom in here. Again, we said on the x-axis we have the false positive rate, which is the cost incurred by the model. On the y-axis we have the reward or the benefit. Obviously, we want the model to be, ideally we want it to be here at the top, at the very top left in this particular graph. Because the higher up the y-axis and the farther away from the right, its true positive rate will be 100%, and its false positive rate will be closer to 0. Now, if you look at this diagonal line, this is any model that falls across this diagonal line is a model that is random. It randomly classifies something to be true or false. One more thing that is not indicated or labeled in this graph and the other ROC graphs that we will see is something we call the threshold. The threshold here is also called the score. Excuse me, the threshold is also the accuracy. You see, if I scroll back up here, there is a metric that combines the precision and recall. The accuracy is supposed to be the average of precision and recall. You can see here in the denominator we have positive and negative. Okay, so if we want an accurate model, then we are increasing the threshold. But what happens is when we increase the threshold, we will reduce the false positive rate, but we are also going to, in some cases, decrease the true positive rate. So let me see if that graph is listed in a different section. Yeah, it's this one. I'll come back to it in a moment. But let's continue with this section first. So we have the model C here, which is not a good one because it's random. It guesses things randomly. It's like flipping a coin. The more optimal ones are A, B, and D. Obviously, the most optimal one is D. Now, one more thing you'll notice is the model E. The model E is clearly suboptimal because it has a much higher false positive rate. But in a way, it can be better than the classifier C. Why? Because the model, this classification model E, has some valuable information. There is some pattern here. It is consistent. It is more consistent than C, but it's just consistently wrong. So it does have some information, but we could hypothetically flip it around. So we'll end up in this section, in the on the other side of the diagonal. So somewhere up here, for example. So this is still the model E is still useful in some way. We just have to find out why it's consistently wrong. So later on, towards the end of the paper, where it talks about the interpolation of classification models, we want to take this into consideration. Okay, let me see if there's anything else I missed from this section. Nothing that I haven't pointed out yet. Okay. Yes, also the paper uses the words conservative and liberal. To give you context, let me take you to the subsequent section. So when they say conservative, this means a model that has to which there has been a higher threshold. So we expect the model to be more accurate. And liberal is when we reduce the threshold. So let's look at the next graph. Okay, over here. So if you see here, these are this is the performance of the model of let's say I think this is one particular model that has been given different thresholds. So here by score, we mean the threshold, like how much we demand from this model. If we want it to be 90% accurate, all the way down to 10% accuracy. So all of these points that you will see are ranked in order of threshold. If I scroll down here, what this graph is showing you is that when you set the threshold very high, okay, 90%, yes, the false positive rate is significantly. I mean, it's all practically zero, but also its true positive rate is also down. What we want to do is get the model, and of course, if you see for this particular model, as we reduce the threshold, as we go from conservative to liberal, it it does rise in its true positive rate, but it also starts to incur a higher cost. So much so that when we bring the threshold down to 1, its false positive rate and true positive rate is 100%. So practically it's random. So that's not very good. This is one of the things that the ROC allows you to perceive. You're able to take samples of this classification, this model's predictions, plot them around the ROC curve, and see how it performs across different thresholds. So you can see, hey, if we increase the demand, is it gonna decline or is it gonna increase? Because there are some cases where you don't necessarily need 100% accuracy, or 100% accuracy is actually not realistic. Still, you want to get to a certain threshold. So let's say 70% accuracy, 75% accuracy. And so this model will allow you to observe that. So if I scroll up here, you can see when we set the threshold to 38%, 37, 36, and 35, the accuracy doesn't increase. It's still at, 80%? But it does incur a higher cost. If you see this section here. So if we will get an 80% true positive rate at 38%, there's no need to decrease the accuracy threshold anymore, because it's not going to help us any further. And if we drop it below 35, yes, we will go from 80% to 90%, but look, the false positive rate is 80 to 90%. So that's random, not any good. So if we look at this, if your goal is to reduce the false positive rate, this vicinity could be ideal. So if you let it at 54, your true positive rate would be 50%. If you're willing to accept a higher cost, you can go with 38. But again, it really depends on the domain. It depends on the domain, like how problematic will it be if you misclassify something. If it's a shopping, like an e-commerce website, and you misclassify the next product that the customer may want to buy, it's not so bad. But again, if it's medical diagnosis, again, you may want to spend more time with data munging and even looking at different models, which is again something else you can do with the ROC curve. Okay, so if you want to analyze a machine learning model's performance for different accuracy thresholds, ROC curve is one way to do. Is one important metric. Okay, let's continue. Uh, I'm just glancing through this section to make sure I did not miss anything else. Yes, another section, another important part is here. How do you choose a threshold? More empirically, the paper says that we could use a training set to estimate a the prior distribution for the data set. So, what percentage of uh, yeah, so we can calculate the problem. Now, if you want to calculate the prior, you actually do need the labels of of the data set to be able to do this. Okay, and of course, it points out that there will be some data sets which will not have properly calibrated distributions. That means when you add up all of the values in the uh, distributions, they don't add up to one. So a proper distribution is one where if you were to add up all of the components of the vector, they would add up to one. Improper distribution is one that does not add up to one. And if this is still not clear, I'll show an example where you might have a vector corresponding to a distribution that is improper. This can happen if you're doing something like topic modeling, like an information retrieval or search engines. Okay, let me continue. Let me see if there's anything I left out. Okay, class skew. Okay, let's go. Here it points out something else that I said at the beginning. Large class skews and large class distributions may seem contrived and unrealistic, but they do happen. Again, class skews are like in situations where something may happen infrequently, but they do happen. And large changes to class distributions. What kind of scenarios do you think would cause a large change in the distribution? By the way, change in distributions is a very important component of something called MLOps. Anyone heard of machine learning ops? Anyone looked into machine learning operations? If you're a data engineer, this is something you want to be careful with. Changes or shifts in class distributions, or also known as a concept drift. Can anyone of you give me an example of a scenario where there can be a large shift in the distribution? Okay, and I'm just noticing some comments. Can we get the link? Yeah. By the way, this session will be recorded, and the link will be put on Slack and on YouTube. So yes. Can you also comment on the use of the ROC curves in the case of imbalanced classification problems? Which one is better and why? Can you tell me what do you mean by PR and imbalanced classification problems? So I'll give you an example of where you might have large change in class distribution. Stocks, right? Or just the financial market in general. It could be that one part, or let's say in the first decade of a particular decade, stock prices and technologies might be might be skewed in favor of tech stocks. But then let's say we have some sort of extreme natural. I don't want to get too dark, but volcanoes do erupt, meteors do hit different planets, and then suddenly tech stocks, maybe they're not so important, but stocks in agriculture and essential commodities, we will have a change of distribution that is skewed in favor of those distributions. So in whether you have a skewed distribution or you have changes in distributions of your data over the progression of time, ROC will still be effective. It's not going to be affected by. There we go. Ron Schneider, thank you for those. Refineries blow up, wars break out. Exactly. I mean, these are things that do happen. They happen infrequently, but they do happen. Okay, so by PR I mean precision recall curves. Yes. Now, Chitwan, this paper does talk about that, so I'll answer your question when we get to that section. Okay, so again, substantial change in classification are not unrealistic either. Yes, I mean, we can see that we can see it right in the news every day. So medical decisions, making epidemics, exactly, yeah, and fraud detection, proportion of frauds, change in manufacturing, exactly, like Ron says, in refineries can blow up, or things happen. Yeah, so let's look at this. Let's also look at this figure. This is close to what you asked, Chitwan. So here we have. Now this plot is taking something else into consideration. This table is taking something else into consideration. So by the way, we have more notation. P is the actual class. Excuse me. P is it predicted or is it Y? Let me actually scroll up to remember what it was. Again, this is a lengthy paper. Is improper to one. Why is it the predicted one or is it the actual? If I scroll down this paper, I think I wrote it somewhere, by the way. Oh, here we go. One thing I do when I take notes is always look out for the expressions. Here we go. Many clouds. Yeah, so the y and n are the ones that the model predicts. The y and n, the n's are the ones that the model predict. Thank you, Alson. Yeah, the capital N is the one the model predicted. So lowercase p, lowercase n are the actual labels. Uppercase y, uppercase n are the ones that the model predicted. So you can see when the model predicts true and the original label is true, that's 100%. It's almost 100%. And if you look down, I think at 7 and 8, you can see 2 of the classifications are incorrect. Now, this paper, let me see the section where it was talking about what this. Yeah, so I think it's the comparison of the accuracy and the graph, because this graph takes into account the false positive rate and true positive rate, whereas this takes into account accuracy. Let me actually jump to that section. Where do we see figure 4? Figure 4. I'm just going to use figure 4. Yeah, so it says here, consider the simple instance scores in figure 4, which comes from naive Bayes classifier. Now, the particular model is not important. Comparing the hypothesis against the true classifier, you can see the classifier gets it 7 and 8 wrong. So 2 out of 10 of the labels are incorrect, yielding 80% accuracy. So if you were to look at for example, if you're using TensorFlow or PyTorch and you look at the metrics only numerically, you will get 80% accuracy. But if you look at the curve, the ROC curve, you will get a different story. So it says, however, consider the ROC curve on the left side of the figure. The curves rise vertically from 0.1 to 0.1 to 1.1, 0.1. So it goes up here. And then horizontally from 1 to 1. So why this discrepancy? It says measuring. Yeah, so it says here that the ROC curve shows the ability of the classifier to rank the positive instances relative to the class instances. So it's relative. And it is indeed perfect in stability. Accuracy measure if the scores were proper probability. Now, this is a very good point. Here's a highlight. It says the accuracy measure would be appropriate if the scores were proper probabilities. Meaning, if you were to add them all up, you would get 1, but they are not. Let me actually stop here and give you an example of an improper distribution. Let's say, for example, I'm going to type here sparse vector, like in the case of NLP. And if I can't find one, I'll show you. I'll just make up an example. Okay, let me give you an example. Let's say you're trying to classify documents. Okay, this is which section? This is section 4. Sorry. Section 3 was what? Section 3 was for the ROC space. And section 4 is for curves in the ROC space. Okay. Let me give you an example of proper and improper distributions, but the paper uses the words probabilities, so I'm going to say probabilities. If you watched the first episode, I give you an example of word vectors. So for example, in NLP, the way we said that in all examples of machine learning, your input must be represented as a distribution. So whether it's word or sound or pictures, whatever, it has to be the form of a distribution. So let's say we have some words like dog and cat. Dogs and cats have different characteristics, so they also have different distributions. So for example, you can have something that looks like this. 0.5, 0.3, and then 0.2. So 50% probability, for example, that it's a four-legged mammal. 3% probability that it has, I don't know. What could it be? The size of its, what do you call this part of not the nose? I forgot what it's called. But the shape of the head, right? The length of its face. And 2 could be, let's say, its lifespan. So if we compare that to the cat, okay, 50% that, 20%. This will be much smaller. Like, let's make it 1. Actually, I meant to make this 3. Let's make this 0.5, and let's make this 65. Oh, sorry, I meant. Okay, so this is the distribution of the cat. This is the distribution of the dog. Now the numbers that are important. The fact is, if you would add up all of these numbers, this would add up to 1, and this would add up to 1. This is a proper distribution. So what that paper is saying is accuracy is a good metric assuming your distributions are proper. But there are examples in machine learning where we have improper distributions, like in topic modeling. For example, let's say you have a blog and you want to know what kind of blog is this? Like, is it, what kind of web page is it? Is it a wiki page? Is it a news article? Is it a blog? Is it an Instagram page? Like, what is it about? There are too many classes. And because there are too many classes, you do not want to have a vector with many zeros in it. So it would look something like this. Let's say you have some sort of blog. Its distribution could be 0.4, 0.1, and then, 0.2. If you add these all up, they don't add up to 1. Because the probabilities are so small across all of the other topics that they don't even make sense to include. Some topic modeling machine learning models do this. Like if any of you have used Gensim, which is used for text classification, you will get a sparse vector or a sparse matrix like this. This is an improper distribution. Accuracy, if you were to do a machine learning model and look at accuracy alone, it would be inaccurate when it comes to distributions like this. So for the entirety of your data set, your metric is flawed, but not for ROC. Okay? Now, that doesn't mean you should eliminate accuracy altogether, but it just means that you always want to look at multiple metrics simultaneously. So do this and do that. Now, what are we highlighting here is, again, the accuracy threshold. When we decrease the threshold to 60%, we start to incur a false positive rate. And we bring it down to 50%. Again, our true positive rate, I mean, we're not making any further improvements. We're just incurring more false positive calls. So it's a good idea when you have a graph like this to see when it converges towards one on the y-axis, and then stop reducing the threshold any further. Okay. All right. Let's continue. Yes, here we go. Oh, okay, I think Chitwan, this is the part that answers your question actually. Comparing the ROC curve versus precision and recall. Okay. This is that section that is relevant to your question. Yes, thank you, Ron Snout. Yeah. So if you see here, let me make sure I remember which graph, these graphs are, but it is definitely comparing ROC versus the recall. So if I scroll up to here to see the effect of the class skew, right? So when you have a skewed class, right? Some data distributions are normal, like when you're looking at the income of people. If you were to plot the income of people, it will be normally distributed. Okay, most people make average. Even if you were to take a company where all of the employees are, make a lot of money, even in that context, you would still have a normal distribution where the average of people, most of the people would make average. And the number of people who make a lot of money and the number of people who make very little money relative to the mean average of that company, you would have small numbers. So you will get that bell curve. So what this section is trying to illustrate is the effect of class skew when using the ROC curve versus something like the PR curve, the precision recall curve. Two classifiers evaluating ROC and precision recall curves. In figure in A and B, the test set has a balanced 1-1 class distribution, which means that the number of, if you're doing binary classification, the number of classes are equivalent. Graph 5C and D show the same two classifiers. 5C and 5D. So let me see, what was this again? The test. Yeah, so if you see here, A and B show how the curves behave when the classes are balanced. They're not skewed. And the below figures show you how the graphs perform when you have skewed class. So for example, this could be incomes of people, which is not it's normal distribution, not something that is very ordinary. Whereas this one could be something that has to do with fraud or a disease incidence, which, like I said, is an example of a skew distribution. So if you compare the recall curve versus precision recall, you can see it remains resilient. It doesn't change. Whereas when we use the same precision recall graph on a skew distribution, it's all over the place. In particular, let's see what it says here. It says while the precision recall graph in 5b and d differs substantially. So this could be the same model. This could be the graph of the same model. But because the same model is working on two different types of data, the graphs are giving you two very different pictures. Like the model could be a very good model. Like I don't think it's stated which data set this is. Maybe decision tree, or it hasn't specified. But I guess that doesn't matter, because if you were to use a random forest classification model, if the data was balanced, if it was, let's say, normal distributed, yeah, the curve would give you good, would look good. Whereas if the class was this skewed, let's say in the case of, like I said, fraud or disease, it would look terrible. So you might be compelled to say, all right, maybe this is not the right model for our situation. Whereas if you had used the ROC curve, you would have gotten a very different picture. So when it comes to, so far, what have we learned? We have learned that the ROC curve is useful for making use of machine learning models that are non-random, but they make consistent mistakes, which means the ROC curve will indicate to us models from which we can learn something useful. We have learned that ROC curves can show you how the machine learning model can perform across different thresholds. We can actually plot that. And now we are seeing how it performs against, we have seen how it performs against precision, recall, and accuracy. So typically, many tutorials online and many literature highlight these three metrics: precision, recall, and accuracy. But as we can see here, it's not, these metrics are not sufficient for all kinds of data, for all kinds of distributions. Okay, let's carry on. So that's section 4, creating scoring classifiers. Now, I think this section 4 has to do, so this algorithm is for section 5. I'm not going to take you to the algorithm, but the section 5 is for, it's for either averaging, let's see what it says here. Let me look at the graph first. Okay, so figure 6. Let me also look at my notes. Again, there's a lot written in here, so I need to make sure. Section 5 has to do with, so the section 5 is the algorithm, which I'm going to skip for now. Section 6 has to do with the convex hull. And the convex hull allows us to look at a probabilistic, make a probabilistic interpretation of the ROC curve. Okay, so before I take you to section 6, let me see if I can highlight anything important from section 5. So this is going to sort the classifications by their score. Okay, yeah. So this algorithm is for generating the curve. First, what it says is, what we will do is, if I scroll up here to this example, the algorithm below is for taking this list of classifications, then using the merge sort algorithm. The merge sort algorithm is a logarithmic model, n log n, which is it's a merge sort is better than a linear reordering. But the algorithm is about ordering these classifications by their score and then plotting them. So if you want to produce a curve like this is the algorithm that you want to look at. Now, we haven't covered pseudo algorithms yet, and I'm not going to go into this now. Maybe later on when we have I'll give you a tutorial on pseudo algorithm but that's something different. By the way, for ML paper 1, I'm going to, if I don't know if you've watched it or not, but even if you've watched it, there are some important details that I just couldn't cover in a span of 1 hour and a half. Things like the TSNE and the Bayesian theorem, Bayesian theorem and conditional probability. So those will be like, I'll record a separate video, and those will serve as appendices to ML paper 1, and for that matter, any other paper that we'll cover. And I'll do the same for pseudo algorithm, okay? But nonetheless, I give you the important part of this algorithm, what it does. Okay, so let's skip ahead and come down to section 6. Is figure 6 relevant? Is section 6 about figure 6 or not? I just want to see to which section this figure belongs. Yeah, okay, it's still about section 5. Okay. And I think this has to do with averaging. Yeah. Yeah, so what's going to happen in this algorithm, you are going to get... Is there any sampling done in here? Efficient. Okay, I see what this is. This is about... so the algorithm also takes care of situations where different thresholds produce the same accuracy. Excuse me, the same true positive rate. If you remember in one of the figures, I showed you when you reduce the threshold, in the originally you may want to consider reducing the threshold is to gain a higher true positive rate by sacrificing and getting some false positive rate. Now, so again, if I come back up here in this section, right, in this figure, you can see there's a general trend. As you decrease the threshold, you get a higher true positive rate, but you also incur a higher false positive rate. In this example, in this section up here, when we reduced the threshold from, let's say, 90% to 54%, we got a true positive rate of 50%. But we dropped it down to 53, and we dropped it down to 52. Again, we only incurred cost with no benefit. So this is what this paper is trying to show us. This is what this graph is trying to show us. This algorithm, rather. How to deal with situations where you reduce the threshold, but you don't get anything you gain nothing from it except more cost. Similarly here, you're reducing the threshold, but you're not incurring any cost. You're only gaining and gaining and gaining. Now, what this algorithm will do is we want to produce a curve, not a scatter plot. So it will handle these situations where you have what's the word I'm looking for? Points that keep falling on the same points that keep falling on the same point on the y or x axis, and how we can collapse them into a single line. All right. And then here, yeah, so this ratio is about handling not regression, not quite. I guess it could be analogous to regression, but not exactly, because regression does something something else. I guess, yeah, I mean, you could consider these to be the residuals, but I don't want to use regression as an example. Also, this was something I don't want to forget. This equation had to do when you have skewed distributions, like when you have like 10 times more of one class versus the other. Let me see if I can remember what this was about. I think this is in a different figure. It's down. Sorry if I'm scrolling up and down too quickly. I just don't want to. I just want to make the most of time. Make the best use of time here. Uh, okay, this has to do with the convex hull. So let's actually jump to that convex hull. Let me tell you what this graph is about. But first, let me give you a definition of convex and the word hull. So I'm gonna show you a convex from Google Images. I will give you the informal definition just to get past this point. So if you have a set of points and you take in some set, so all of these red, dots you see, these are all points in some sort of space, and a space is a set. So if we would take all of these points in the set, including the and draw, if you like, if you put like a rubber band around all of the outermost points, you would get a convex hull. But let me also show you, see if I can find a formal or more formal definition. Type here formal. Yeah, so this is the idea. The convex hull includes also the points in that space. So the same analogy I gave you. If you take all these points, you put a rubber band around all of the points, you will get a convex hull. That's all it is. Now let's see why that's even important. If I bring you back to the paper, you can see that we have A, B, C, and D. These are the ROC curves of 4 machine learning models. Okay. The most optimal ones are A and C. If we take all of the points on the A curve, all the points on the C curve, then we can interpolate them to produce the convex hull. And the convex hull is the upper part, is the part in the white, this white part. Let me see that section where we're summarizing. Let me scroll up a little bit. So 1 second. So it says here, since only the classifiers in the convex hull are potentially optimal, because you can see here D is, well, clearly you can see it has a very high, relative to the others, it has a very high positive rate. It's almost random. So this is a suboptimal model, and the relative to A and C, B is also not as optimal. But let me see this the summary here. Okay. Now this curve is actually this plot actually has to do with skewed distributions. So for example, let's say again you have a data set where you have 10 times more of one class versus the other. So if we were to plot let me just look up that section, make sure I'm not going to mischaracterize this graph. Section 7, figure 7.8. Figure 7.8 says what? Where is figure 7.8? Figure 7.8. 7. Okay, B is not optimal. Okay, and since the convex hull is bounded only by points from A and C, we can eliminate B and D, and yeah. So the second graph is not very clear because it has to do with, it says consider a scenario in which the negative outnumbers the negatives outnumber positives 10 to 1. Okay, so I'm not sure why it is angled this way, but I guess it's just an example. But this it calls this line the ISO performance line, and the ISO performance line again refers to the line we saw up here in the very start of this presentation, the one across the diagonal. Okay, so anything above this line is better, and anything below the is better than the baseline, and obviously anything below the line is inferior than the baseline. If you come back here, the line alpha is the ISO line for models to which we've assigned one particular threshold, and the line beta is the ISO performance line for models to which we've assigned another threshold. And specifically, let's see if this paper mentions what the thresholds are. Does it say? No, it's the same threshold, but when we have different conditions. So, for example, for alpha, if the negatives outnumber the positives 10 to 1, then we have this line. But if it's 1 over 10, we get this other line. The point here is this: you will know that your model is optimal if it falls across these points, and then you can also interpolate these points, so you can actually connect alpha and beta together to create a curve, one that you would see here. Now, let me also talk about this part, and I'll try to wrap this up quickly, so let you answer any questions. This has to do with area under the curve. Now, area under the curve has to do with measuring the area under the curve, obviously, using like a definite integral. If you see here, this is a unit space, unit coordinate space. So it goes from 1 to 1. And this works out nicely if we're trying to know probabilistically how any particular classification model will perform. So if you see here, we can clearly see that the model B has encompasses more of this area than A. So because its area is larger, its performance is also better. Now, if you want to see how this, first of all, how it's evaluated and why it's the case probabilistically speaking, we would have to talk about a few things. Namely, we would have to see how we can derive the definite integral of the curve, but it has to do, but it's analogous to the probability density function. That's number one. Number two is the Gini coefficient or the Gini index. Okay, so I'm going to skip that. I'm not going to go into more detail for that, but you can actually accumulate the region for the area under the curve, area under a curve of uh, two models. Now, in the case if you want to compare the area under the curve of multiple models, you would actually plot multiple curve against uh, one model. So, for example, let's say you have 10 machine learning models and you want to compare all of their areas. You would compare A to B, then C to B, and then D to B, and so on. Very similar to what's it called? Like that method from scikit-learn, the grid search. And then there's an algorithm that shows you how to calculate the area under the curve using what we call the trapezoid method. And if you see the formula for a trapezoid, that's how you measure the area of a trapezoid. So this is like it's analogous to the Riemann sum. So with the Riemann sum, you can use different integral to calculate the area under a curve. You can use this algorithm given in this paper to calculate the area under, well, it's not exactly a curve because you have these sharp edges, but as you increase the number of instances, it will eventually become smooth. Okay, but nonetheless, you want to use this algorithm to calculate the area under the curve if you're doing it through programming. Mathematically, you would just express this with a definite integral. Okay, and it says it here. So the graph on the right shows the area for a discrete classifier, and the other one is for a probabilistic classifier. You can see it's more continuous. But this algorithm, I think, works for both cases, for both discrete and continuous classification. All right, let me skip ahead. And here also it talks about averaging ROC curves. So for example, I think this one has to do with, let me see if I remember. Is it multiple models or multiple thresholds? Yeah, so this is for multiple thresholds. Because you see, so far what we have seen have been point estimates. But there are different ways you can configure a machine learning model to get different points. If you're familiar with the idea of a confidence interval, this part is about taking into account the confidence intervals for different thresholds and then averaging them out. So we don't have time to get into confidence intervals now. If you're interested, I have recorded a workshop on this topic. If you go to YouTube, there are 3 workshops on statistics and probability. Look up the one that is for confidence intervals, and you'll see what I'm talking about. What do I mean by averaging out the confidence intervals? And the other graph, the D1. Let me just see if I remember what this was about. This was for, where is D? So this is figure 9. Average by threshold. Yeah, so the fourth one does it for both, for different thresholds and different confidence intervals. So when you are going to produce an ROC curve, because machine learning models are probabilistic, and that is the reason why we use techniques like cross-validation to test the classification models against different samples, meaning we will have variation in how the model performs. We do need to take this into account. So, for example, obviously when you're training a model, you're going to do 2 things. You will have train, validation, and test, but you're also going to use the same model with different hyperparameters. So again, if we talk about a decision tree, you may have different depth, you may have different number of trees, right? Because random forests are a combination of trees. So the different number of trees that you may use, or a different maximum depth you may use for that same model, you might get different uh, true positive rates. So not only will you have different point estimates for different samples of your data, you will also have variation for different hyperparameters of the model. So you need to take this into account. Again, ROC curves, an ROC curve would take all of this into account. The variability of the model with respect to different samples of your data set, and with respect to different thresholds of your different thresholds of your of the fitting. And then, yeah, so algorithm 3 is for the vertical averaging. Number 4 is the threshold averaging. So you want to average them both. You want to take both of them into account. And then, yeah, so section 9 is about ROC curve for multiple classes. So let me just highlight this section for you. If you have multiple classes, so not just fraud, non-fraud, or spam, not spam, or red and blue, you have multiple classes. Again, topic modeling is another example, because any particular web page can fall into 10 classes, 20 classes, 30 classes. So the way this paper expresses it is this: you would take one class, let's say news, and that would be your positive class. All the other classes would be negative classes. And so N here would be the union of all the other classes. So C sub 1 could be blog, C sub 2 could be social media, post, Twitter, for example, Facebook. C sub 4 could be a wiki, C sub 5 could be a personal blog, and so on. And then another important or interesting part of this paper, if I scroll down to the interpolation part, is this. Here we have two machine learning models. You have A and B. You don't have C yet. If you see A has a lower false positive rate. Conversely, it has a lower true positive rate. B, on the other hand, it does have a higher true positive rate, but unfortunately, it also has a higher false positive rate. So you can use a linear programming. Very simple. If I scroll up to this section, you are given a system of equations. For example, this one over here. Okay. Let me run through this very quickly. Yeah, so for example, no, actually this is too long and we only have 5 minutes left. But I want you to look at this section. Hopefully after this session, because it shows you how to deal with how to come up with a third classifier by solving a system of inequalities. This is like something you know covered in linear programming. To come up with a third classifier that makes that has the best of both worlds. That has the high positive rate of the A classification model, and the higher positive rate of the B classification model, but the lower false positive rate of the A classifying model. Now, of course, in practice, you might have more than just multiple classes, but then that's what linear programming is about. In linear programming, you're able to have multiple constraints and solve multiple equations to arrive at what we call the optimization function. So your optimization function will then be your optimal classifier. Okay, now this was a very sped up reading example. Unlike in paper 1 where I had mostly slides, in paper 2 I had to, use the paper itself, because I had to, highlight specific text in the paper, and it's a lot lengthier than the first paper. But we only have 3 minutes left. I still want to give you like 5 or 10 minutes to ask any questions. So if you have any questions, you can stay back, and I'll answer them. So we can go all the way. We can go past. We can go 10 minutes past the session. Does anyone have any questions about what I've just talked about? Anything you've seen here that maybe unclear to you? Because I rather did go through this quickly. Any questions at all? Any comments? Any suggestions for the third episode? Let me scroll all the way to the top. Let me open the chat box to see if you have any questions, by the way. Oh, here we go. Rashmi asks, does this imply for nonlinear structures too? What do you mean by nonlinear structures? Specifically, what do you mean by structure? Yes, exactly. So the whole entirety of section 9 was about machine learning models with more than 2 classes. Like, how do you deal with that? And that's what I was trying to highlight in here. So if you have a binary classification, then you would have P and N. If you have multiple classifications, then you would have one P, but then you would have several N's. So if you're using colors, let's say your default color would be blue, and then red could be N sub 1, green could be N sub 2, orange would be N sub 3, and so on. And you'd basically take now there are 2 things. One is you would be taking the union of those sets, compare them to your default class, and you would have multiple ROC curves. So you would compare the ROC curve of, let's say, class 2 versus class 1, class 3 versus class 1, class 4 versus class 1. So you'd have to visualize all of them. This is also done in correlation. And if you have multi-dimensional data and you're trying to look at correlation, yes, there is a correlation matrix, but you can actually even you actually want to plot the correlation of multiple factors. So correlation of multiple factors. This is not relevant to ROC, but I'm just trying to give you an example, an analogy. Yeah, something like this. Ron asks, interesting question. How long did it take you to read this whole paper? I went through this paper 2 or 3 days ago. Now, can I counter your question with why did you ask that question? Because it's an interesting question. Justina says, can we get a link to this paper? I got this paper from Elsevier, but I did have to use institutional access, so I had to access through my university. I'm going to save this. Let me make sure that it is not. I'm not going to violate any rules, and if I don't, I'll put this on the Slack channel. Speaking of the Slack channel, please join the Slack channel if you haven't already. Let me share the link here, because you'll find the slides, the links. Oh, thank you very much, Alson. This is the link to the paper. Thank you so much. Perfect. Thank you for that. I'll include that in the Slack channel. How long did you How long did you spend reading this paper? Now, here's one more thing, by the way. You can read a paper faster if you're already familiar with the jargon. So right at the start, this paper starts with, statistical jargon. The word metric, the word accuracy, the word cost, the words here, this description, skewed class distribution. Like, if you know what these, if you know what these mean, then you can, move along more quickly. If not, you have to have some sort of reference book So you can look up what is skewed class, what is accuracy, what is precision. So it it depends on your background, really. Any other questions? Any other comments? Let me, by the way, tell you what the third paper is going to be. Learning from imbalanced data, which is a very nice transition because we talked about uh, analyzing machine classification models for skewed data, for multiple multi-class data, and skewed data is imbalanced data. Skewed data is an example of is exactly imbalanced data, and so we want to see how we can learn. We can train a model in scenarios like that. Did you find the symbols used in the equation were consistent with the general mathematics? Very nice question. The symbols, yeah, but the equations, I'm not sure if I would use the word consistent because unfortunately, many statistical equations are not let me rephrase that. There doesn't seem to be a convention for all expressions. So if I, for example, show you accuracy, yeah, this is something very simple. It's just basic arithmetic. There's no derivatives, there's no integrals involved. So very basic mathematics. If I come up here, right? Just addition and division. When I took you to the Wikipedia page, you can see here that not only do we have different ways of expressing the same ratio, we also have different words. So true positive rate or sensitivity or recall or hit rate and unfortunately some textbooks do not even bring this up. They don't even tell you that this has a synonym. You just have to know it. It's if you don't know it, well, maybe read. So this is one of the challenging parts of statistics and by extension machine learning. A lot of the statistical terminology is used in machine learning, and in general, you kind of have to be part of the, what do I say? Not industry, but you have to kind of been exposed to this phenomena that one word can have multiple synonyms and can be expressed in different ways. In this paper, for example, it says that the AUC, the area under the curve, which is a scalar value, is equivalent to something called the Wilcoxon test. So you might come across another paper that talks about Wilcoxon test, and they may be performing the same metric, and you may never know that this is actually ROC. So this is the problem. So it's not so much that the ideas are difficult, it's the fact that there is no standard convention. There's no standard terminology. People use different words, and they use different expressions to express the same idea. And then Ron says, I have run into symbols that having different meaning depending. Yes, that's also true. So for example, in statistics, Greek letters are used for something we call statistics or parameters. Let me actually pause right here to define what these are. I'll open a new file. Now, let me just say this. If you want to go into symbols of statistics, I have a series of workshops recorded on statistics, so you can check that out for detail. But we have the word statistic, and we have the word statistic singular form, and the word parameter. Statistic mean, a statistic could be the mean average, the expected value, the skewness, or kurtosis. Now, this is what we call the 4 moments, but you can actually have higher moments. A moment describes a detail of the shape of the data. Actually, this is supposed to be variance. Sorry. If you know the mean and the variance and the skewness and the kurtosis, this is like drawing 4 dots in a graph. You can draw through the lines, through the dots, and you will know the shape of the data. We have these same words for a parameter. Now, so let me take a step back. This is called a statistic. This is called a statistic. All 4 of these are called statistics. When you're talking about a sample, these same 4 words would be referred to as parameters when you are talking about population. So population is the entirety of the data. Sample is, well, a portion of the data. So these words are not very intuitive. And if you are not familiar with this terminology, it can get in the way of learning statistics and machine learning. So parameter and statistic, these 2 words mean the same thing, but for different types of data. And yes, so speaking of the letters, let me just also add this. So when you are talking about a statistic of a sample, okay, you would use bar X, you would use sigma, the Greek letter sigma. For skewness, actually, I think for the population variance, it's for the population parameters I use Greek letters, not for the statistics. So for the samples, you would use Latin letters. For population, you would use Greek letters. So for example, the mean average of a population would be mu. Again, same concept. Both of these are referring to arithmetic means. But when you talk about the sample, you call them a statistic and you use Latin letters. If you're dealing with a population, you call them parameters and you use Greek letters. So this would become sigma. And in physics, for example, it's completely different. It's a different story altogether. And then if you're talking about statistical physics or statistical mechanics, now you're even adding you're potentially more confusion. Because mu and sigma have different meaning in physics than they do in statistics. So what I would suggest you to do in both, when you're learning any mathematical discipline, is to get yourself a handbook. I have several of them on my desk, on my shelf. So even if you don't have physical ones, you can buy the Kindle version or get a PDF version. So I've always said this in the other workshops: the symbols and the terms are the obstacles to learning mathematics, statistics, or machine learning. But the concepts by themselves are not that, they're not out of reach. Like these ideas that we talked about today, they're all intuitive. Any human being can understand them. But it's the symbols and the terminology that act as barriers. So I would suggest that you look at mathematics and by extension, statistics and machine learning as a language. You're learning a language. You're not learning. The idea is not to memorize equations. It's just to become fluent in this language. Know the symbols and what they mean. Okay, everyone. Any other questions or more comments? If you don't have any questions or comments, we can wrap up this session. Let me just share the Slack channel, link to the Slack channel, because I don't think I did yet. If you have any questions about anything in particular, you can post it here on the general channel, and I'll be happy to answer you. Okay. At least the authors of my favorite book do a great job explaining. Yes, some books do a very good job of including a glossary at the end. So you can always go to the back of the back of the book, see what the symbol means, and come back. Those books are amazing. Hands-on machine learning with scikit-learn. Yes, so I'm also planning on doing a workshop, or rather a series of workshops, where we actually use scikit-learn, TensorFlow to implement machine learning models. Okay, and if you have any other suggestions, please just come to the general channel. I'm very open to suggestions you have about other workshops that we can do here at BigNumber, other topics that we could cover. But until the next workshop, everybody, thank you so much for joining me. And I hope to see you in the next session. For now, enjoy the rest of your day, and bye-bye.